Okay, our final lesson rather for this unit is a two-parter, but I'm just going to go ahead and do it in two pieces, so it's all just in one place. The last topic we're discussing is how two lines can intersect, and if you remember in two dimensions, there were only three options in terms of how lines, or what we call a system of equations, a system of two lines in two space, might work. Either the two lines were parallel and consistent, which means they're coincident, they are the exact same line, and therefore they intersect everywhere. The two lines have different slopes, and therefore intersect in exactly one place, or the two lines have the same slope but are not, they're what we call parallel and distinct, as opposed to parallel and consistent, or coincident, whichever way you want to say it. In this third one, there are no solutions because the two lines never cross. So either you had one solution, or you had infinite solutions, or you had no solutions. Now, of course, all three of those things are still possible in three dimensions. You can have two lines that intersect each other in one place. You can have two lines that are actually coincident and therefore have an infinite number of solutions. You can have two lines that are parallel and distinct and therefore, they never meet. Or you can have this new type of situation, which is here, where the lines are skew. And skew simply means they're not parallel, but they still don't meet. And that could never happen in art in two dimensions, but it can happen in three dimensions, because just imagine you had this same picture here, except L2 is one unit behind the page, and L1 is on the page, and they're never going to meet. Right? They're not parallel, but they're still never going to meet. So again, we can easily demonstrate this. We'll just quickly create three systems that have these properties. So let's make a point A equals 1, 1, 1, 1. Okay, our first direction vector will be 1, 2, 3. Our second direction vector will be -2, 1, -3, let's say. So we have line A with M1 and then line A with M2. Of course, both these are going to pass through that same point A, but they're going to have different slopes. So here would be so these two lines, for example, would cross at exactly one spot. Now, to draw skew lines, right? Imagine we took G, right? Instead of having it go through A, let's have it go through 0, 0, 0 with these same things. Now, let's get rid of the direction vectors, make it a bit easier to see. Now, these two lines do not cross and will never cross, right? You can see the closest they get, is kind of in this region in between the two of them right there. But there's no, they're not going to get closer together as you move farther away out of this picture. So these are an example of skew lines. Okay? You could take this second point, give it the direction vector M1, and now you have parallel lines that never meet. And of course, you could just make them the same line. I don't see why we need to look at that one. You can imagine that pretty easily. Okay, classify each system as having 0, 1, or infinitely many solutions. Alright, consider for this first one. Okay, n normal vector would be 4, -6. And this, would be the normal vector for line 1. Can I just see? Maybe there's an easier way to organize this. Just push this down a bit. No. Okay, in that case, what we should do is we'll make a table. Alright, then we're going to go, n2 so the second normal vector would be 6 and -9. Now you can see here that n1 equals k n2 because you could just, let's just say in brackets here, if k were equal to 1.5, right? So 4 times 1.5 is 6, 6 times 1.5, -6 times 1.5 is -9, right? So you can see they're parallel. Okay, so we're going to go L1, I think this works, parallel, L 2. So there's the little sign for parallel, right? So the two lines are parallel, and therefore, right, either they are the same line and they have an infinite solution, so they must either be the same line I thought that would work. Okay, infinity. How do you make infinity? INFTY, so they just shorten it. Okay, so they must either be the same line where you have an infinite solutions or distinct and they have 0 solutions. So again, an easy way to check this is to check a single point. So for example, on L1, we know that the point negative 2.50 must be on the line. And again, all I did there was sub in y equals 0 and solve x, right? So if y is 0, then this whole thing is like temporarily not there because it's equal to 0, right? So 4x equals negative 10, so x equals negative 2.5, and that would be your x-intercept. Now try that in the second line. 6 times negative 2.5, take away 9 times 0, is equal to negative 15. So then we check negative 2.50 on L2 and find that it is there. Now, if they share one point and they are parallel, they must share all points. So if they share one point and are parallel, they must share all points. So we conclude there are infinity, INFTY, solutions. Okay, so what does it say? Infinitely many solutions, right? So how did we do that? Number 1, we showed they're parallel. Number 2, we showed that a single point is shared. By the way, if you showed that a single point is not shared, that would be enough to say that there are no solutions, because two lines that are parallel but that do not have a point in common will never have a point in common. Okay, so we look at the next one. Again, let's just copy the format of what we did here. N1, the first normal would be 2 and 3. The second normal would be 1 and negative 2. Immediately, you can come to the conclusion that the normals are not parallel. Okay, therefore, and again, I'm just going to write this out technically, but you can obviously just write it in language. I'm just going to put a little strike through. So it's not the case that L1 is parallel to L2. Therefore, there is one solution. Now, it doesn't actually ask us to find the solution, so we're not going to. You could find the solution. What you would do is you'd isolate x in equation 2, sub that into equation 1, and then solve for y. But here we're only trying to classify, so we know there's one solution if the normals are not parallel. Once again here, I'm just going to literally copy and paste this exact same thing. Because these normals are not parallel, it's 2, sorry, they are parallel. I'm sorry, I did the math wrong. 3 and negative 6. So they are parallel. Sorry, I should copy this one. So let's get rid of this. All right. So yeah, if you again, it's 1. Sorry. I guess I should actually write down the actual number. So 3 and negative 6. So once again, if k is 1.5, sorry, and it should be, I just realized there's a mistake here. The k should be on this side. This doesn't really matter, but just so that you're not confused when you look at this later. It's because it's k times the first vector is equal to the second vector, not the other way around. Still, all the same points are true, but just want to make sure I actually do the right thing. Okay, so L1 and L2 are parallel. So what we're going to do is we're going to check a single point. So let's go with the first one. Looking at the first one, I can tell that the point negative 50 is on L1. Right? Again, just force y to be 0, and you'll see that x has to be negative 10. If we check that on the second line, right? The second line would have, if we force y to be 0, and x would be negative 2. There are no solutions. So they're parallel, but they have a different x-intercept. Now, as you know, a line cannot have more than one x-intercept, and it can't. So I mean, if it passes through at -5, it can't also pass through at -2. These points are not on the same the same set of lines. So again, we'll just quickly draw all three of these, so we can just do a quick reminder of what it is that they look like. Okay, so 4x minus 6y equals -10. And then we have 6x minus 9y equals -15. Of course, they are just, in fact, the same line. So, I guess we can just make a quick. Okay, well, I don't know. I guess I can add the pictures after, but. Okay, it's 2x plus 3y minus 30 equals 0. Okay, and then x minus 2y plus 13 equals 0. Okay, again, you just see they intersect at 1 place. And this last one, 2x minus 4y equals -10. And 3x minus 6y equals -6. Again, you can see when they reduce to different equations. And of course, if they reduce to different equations, they're not going to in fact be the same. They'll be parallel, but they'll be distinct, right? So it'll look something like that. All right. Determine whether the following pair of lines are coincident, parallel, and distinct, or intersect at one point. All right, so this would be the same idea as the one we did above. The difference is we're in vector form here, as opposed to in scalar form, the way we were above. So how do you check if things are parallel or whatever in this case? So again, in the first case, let's do something like this. Okay, so I'm not going to say n this time, so I'm not talking about the normal. I'm talking about the direction vector. So the first direction vector was -3, 1. The second direction vector is 1, 3. So these direction vectors are not parallel. In fact, they are perpendicular, but I don't think that matters for the question, but just to remind you. Therefore, the first line is not parallel to the second line. So as soon as you see that, they must intersect at one location. And we actually, again, we don't need to solve it, but if you did need to solve it, what you would do is you would make up parametric equations. It might be good to actually solve this. Do we? Yeah, I think we have to. Do we ever have to do this in 2 space? Not really. We'll do it in 3 space in a minute anyways. So they must intersect at one location if they're not parallel. Now, the second one, they are parallel, so let's grab them here. Okay, so the first direction vector is -6, +8. The second direction vector is 9, and then -12. Now again, it doesn't really look like they're parallel, but they are, right? And again, the k value that would join one to the other would be -1.5, right? -6 times -1.5 is 9, and 8 times -1.5 is -12. So they are in fact parallel. So now what we need to know is, do they share a point? Now if you look closely at the point, 1, 2 and 1, 4 cannot be on the same line. it's very straightforward. 1, 2, let's just again, if 1, 2 is here and 1, 4 is there, there is no way that two parallel lines here could ever be the same line, because they're distinct at this point. If they're distinct at this point, they must be distinct everywhere. They are distinct, and therefore there are 0 solutions. Okay, again, I'm not going to bother drawing these ones. I mean, you can draw them if you want, but we don't need to. They intersect at one location, therefore there is one solution. Okay, so whether the lines are coincident, parallel, and distinct, or intersect at a point. So these are, let's say, parallel and distinct. So that's what those two lines would be. All right, now how do you do this when they're in 3D? Okay, so you can see here we have the first line is in vector form, the second line is in parametric form. Now notice, I want to make a point about this. Notice that when you have two lines, you use different parameters for each line. So don't use, t for both of them. Use s for one and t for the other. Okay, so don't use, do you notice one of them it has an s, right? Really, we should say after this s in real numbers, and under here we should say t in real numbers. And you can't use the same parameter, so make sure you use a different parameter for each line. Okay, so then what we're going to do here is we're going to say convert both to parametric. So the second one's already in parametric, but let's make L1 in parametric. So we make one of these big brackets, curly bracket, and then a matrix, and then we do the 3 parameters. So x is equal to 7 plus 2s, y is equal to 2 plus 1s, and z is equal to -6 take away 3s. Right? So that would be your parametric equation for line 1. Now what you do is you use the two x parameters to get t in terms of s, or vice versa. Okay, so let's go with, let's say 7 plus 2s is equal to 3 plus t. Okay, and again, where am I getting that from? Let's just quickly use some colors here to demonstrate. So if I take the x and put it in red, and then this x and put it in red, that's what I'm setting equal to each other. Okay, so again, you can come up with a really easy equation here. You just go t equals 4 plus 2s, because you bring the 3 over to the other side, you get 4 plus 2s equals t. Okay, now we're going to use this value of t in the two y parameter equations. So let's use the y parameters. 2 plus s equals 9 plus 5t. Okay, and again, just so we can try to follow this a little bit, let's put this one in blue, and this one will be in, oh my, blue as well. Okay, so now what I'm gonna do is I'm gonna replace t with what I know t to be equal to. So 2 plus s equals 9 plus 5, 4 plus 2s, right? And then I just solve for s. So 2 plus s equals 9 plus 20 plus 10s will bring 27 equals -9s, and therefore s is equal to -3, right? Let's make sure we did this right. If s is negative, well, let's figure out what t would be. So then we know that t is 4 plus 2s, t is 4 plus 2 times -3, t is equal to -2. So let's see if -2 and -3 work in the two equations we came up with. Okay, so let's say check in the first equation, the one with the x parameters, or let's say the one made from the x parameters. So we go 7 plus 2s equals 3 plus t. 7 plus 2 times -3 equals 3 plus negative 2. And we get 1 equals 1. So far, so good. You could check it in the y's as well. It's 2 plus s, so 2 plus negative 3 is negative 1. And then 9 plus 5t would be 9 plus negative 10 would also be negative 1. So we're good. Now, this, up to this point, the question should always work. Okay, so I mean, unless they're parallel, which I actually should have checked before I started this, but I think it's pretty clear they're not parallel, since this direction vector is 1, 5, 5, and this is 2, 1, 3. I mean, they're just not scalar multiples of each other. So up to this point, the question should always work as long as the direction vectors are not parallel, which really should have been my first step. I just assumed they wouldn't be parallel because it says find the intersection. But anyway, this should say if they do not meet, by the way. If they do meet, then we know that they're okay. Anyway, so should have been my first step to check they're parallel, but they're not parallel. So what I'm trying to say is, whether they're skew or whether they intersect, what I've done from here to here will always look like it's working. The final check, right, to check whether they intersect or whether they are skew, check your s and t values in the z parameter equation. Okay, so let's go back up and look at z. My parametric equation for z was negative 6 take away 3s. Negative 6 take away 3s. The original parametric equation for z was 13 plus 5t. Now we know from working before that t has to be negative 2 and s has to be negative 3. So let's check. Negative 6 take away 3 times negative 3 is equal to 13 plus 5 times negative 2. On this side we get positive 3, on that side we get positive 3. So what I'm going to write now, okay, since a pair of st, right, like a pair of parameters, s and t, work in both, let's say make both lines equal, the lines must intersect at that point. Let's observe this, okay? Let's go back to L1. Let's just write the equation for L1 again. So it was 7 to negative 6 plus s to 1 negative 3. Now, the point of intersection occurs when s is equal to negative 3. So let's sub in negative 3 into this equation. Okay, so what happens? We get the point is equal to, this shouldn't be L1, sorry, this should be POI. I'm just going to shorten it to P, but whatever. So 7 to negative 6. Now, take away, or let's say add, I'll just add negative numbers, negative 6, negative 3, and positive 9. Okay, so P equals 1, negative 1, 3. Okay, now again, this is overkill, but let's demonstrate that L2 could also get you there. So L2, let's write L2 in vector form quickly, would be 3, 9, 13 plus t 1, 5, 5. We said POI occurs when t equals negative 2, so P would be equal to 3, 9, 13 plus, plus, and then let's say negative 2 times 1, 5, 5. So P is equal to 3, 9, 13 plus negative 2, negative 10, negative 10. So we get 3 plus negative 2 is 1. 9 plus negative 10 is negative 1, and 13 plus negative 10 is 3. So notice that no matter which way I go about it, I get the same point of intersection. Again, you would not need to do both, just one would be fine. I just wanted to show that they both, in fact, work. Okay, so find the intersection of each pair of lines. So we've done that. We found that they intersect, and they intersect at this point 1, -1, 3. I'll just write up here, optional to check on L2. Okay, you don't need to. All right, so there's that's a one intersecting lines question. Right now, I've kind of done like all the possible work you could do. You'll be able to do this quite a bit faster than I just did, but I just want you to have a good solution for your notes. Okay, the second one, right? The second one, again, the first thing I should do always is compare M1 with M2. And what you see here is that M1 is equal to M2. And if they're equal to each other, yikes, M2. Therefore, the lines, therefore L1 parallel L2. Okay, so we know that right off the bat. So our choices are they either intersect everywhere or nowhere, right? So either every point is in common or no points are in common. So the easiest thing to do here is try to express the point on L1 using the parameters. Well, let's put it this way: sub the point into the parametric equations for L2, and that's just the most straightforward way you could do this. So observe, L1 has the point 5, 11, 12. L2 has the following parametric equations: x equals 1 plus t, y equals -9 plus 5t, and z equals 9 take away 2t. Let's solve the first point. X equals 1 plus t. So 5 equals 1 plus t, therefore t equals 4. If we look in the y coordinate, it should say 11 equals -9 plus 5t. Again, t would have to be 4 for that to work, because 5 times 4 makes 20, and -9 plus 20 is 11. We go to the z. The coordinate is 9 equals 9 the coordinate is 12, and then we have 9 take away 2t is the parameter equation. To solve this, you'd see that 21 is -2t, and therefore t is equal to negative 10.5. So again, since the same t parameter since we cannot show that 5, 11, 12 is on the line, is on L2, let's say, and then I'm going to say since the three parameters do not agree, the two lines must be parallel and distinct, and therefore never meet and have zero solutions. Okay, again, GeoGebra is your friend for this. All you got to do to check or something like this, you do it, then you check and make sure your conclusion's right. So what we're going to do here is we're going to make 2 points. Okay, P1 is equal to 5, 11, 12. M1, which is the first direction vector, is 1, 5, -2. P2 is 1, -9, 9. And M2 is really just the same thing as M1, but we'll type it out anyway. Now, L1, so we'll go line that passes through P1 with direction vector M1, and then we'll make a line that passes through P2 with direction vector M2. We'll zoom out a little bit so we can see them, and then you can be confident in your conclusion that these lines are in fact parallel, but they are distinct and therefore do not meet. Okay? Find the value of k for which the lines do not intersect. This is a bit of a strange question. there are all kinds of ways the lines could not intersect. I mean, so let's make an obvious remark about this one. If k equals 0, right? Well, okay, never mind. Maybe this isn't such a bad question. So if k equals 0, then the two lines are parallel. Hopefully you can see that, because you can see that if you double this direction vector, you would get this direction vector as long as k is 0. And the points cannot be in common. Can I say this? Let me pause and think about this for a sec. I was going to say the points cannot be in common since, you know, when x equals 2, they have different y and z, and the direction vector include x movement. So if it didn't move in the x direction, then it is possible that these two could be the same, because they would kind of like all be at the same spot. I'm not actually sure. I should probably just stop talking about that. But anyway, if k is 0, we can see the two lines are parallel. And let's just quickly draw them so you can see what I'm talking about. So point 1 is 2, -1, 3. Point 2 is 2, 1, 4. M1 is 1, 0, 3. M2 is 2k6. And then let's just say for the time being that k is 0. So we have line P1, M1, and then line P2, M2. And then I gotta stop this animation. K equals, set k back to 0. Now you can see these two are parallel and distinct if k is 0. So let's get rid of the direction vectors, and that's pretty clear. Now, if I change the value of k, sorry, I should bring this back over so you can see it better. If I change the value of k, so let's go graphics, you can see that like there must be a k. There might be a k that causes them to meet, right? And we can kind of like, doesn't look like they meet there. Actually, you know what? It doesn't look like any k is going to help us here, but let's try and show that. So let's try to make them intersect. To do this, let's work with the x parameter first. Okay, so we're going to need a new page for this. Okay, let's work with the x parameter. So 2 plus s equals 2 plus 2t. Okay, so we come to the conclusion that s is equal to 2t, right? Because you subtract the 2 from both sides, and that's all you got left with. Then we go to the y parameter. Sorry, let's skip the y parameter because we don't know k, right? Let's go to the z parameter. Okay, 3 plus 3s equals 4 plus 6t. And we know that s is 2t, so we're going to go 3 plus 3, 2t equals 4 plus 6t, and we come to the conclusion that 3 plus 6t equals 4 plus 6t, and then we show that 3 equals 4. Now, since 3, I think it's like that. No, that not equal to 4, there is no set of parameters that can make this work. Okay, so I said before, if you try to solve this, right, the points are distinct, but the vectors are kind of pointing in the same way, except for the y. And I think what this is showing is that no matter what you do here, there is no way to use an s and t parameter to get these two to line up. Right? And that should make sense, because if you imagine y wasn't even part of this equation and it was just a two-dimensional one with x and z, they are parallel and they are distinct points. So I really don't think it matters what y does in the second equation, since y isn't moving in the first equation. Anyway, I'm not really sure what this question is meant to do, but we can just go through our process and we can say, if they do not intersect, right? So let's try to make them intersect, right? So what I would say is try to make them intersect. If you can't do it, then they can't intersect, and k can be whatever you want. So there's no set of parameters that makes this work. So to give an answer, we're going to say, therefore, k is just any real number. Any real number, and these lines will never meet, right? So k can be whatever you want. All right. Find the value of c so that this and this intersect at one point. All right. This is going to be the same strategy. Okay, so what we're going to do is we're going to start with the x parameter. Okay, so 1 plus 2t is equal to 2 plus 1s, right? Just working with the two parameters. Then we say 2t minus 1 equals s, because you bring the 2 over to the other side, it becomes negative. Then we'll work with the y parameter. Okay, for the y parameter, we have 0 plus 4t is equal to 4 plus 3s. We know that 4 plus 3, we're going to replace s with 2t minus 1. 4t is equal to 4 plus 6t, take away 3, and we'll bring everything over to one side. Negative 2t is equal to 1, and therefore t is equal to negative 1/2. Okay, so then what we're going to do is we go back to the x parameter. Oh my. What's going on there? Okay, x parameter. So back to the x parameter. We have 2t minus 1 equals s. Now we know that t is negative 1/2, so we go 2 negative 1/2 minus 1 equals s. And equals s. And this is negative 1 minus 1 equals s, so negative 2 equals s. So we should. So this is what I'm saying s and t are for this to work. Now we go back to the z parameter, and we see if it works. Okay, so the z parameter is 3 plus tc, right? So 3 plus tc equals 2 plus s. Now we'll fill in everything we know. 3 plus negative 1/2 c equals 2 plus negative 2. Sorry, I know always this was plus negative 2. So we get 3 minus 0.5c equals 0. So 3 equals 0.5c. So c equals 6. So if this is true, then we should be able to show that when c is 6, the two lines intersect. So does it say we have to find the value of c so that all it says is we have to intersect at one point. So technically we're done. If we wanted to know where they intersect, we would plug in the value of s that we got into R2 and find out where it is. So let's just say we had to do this. So point of intersection. So find the point POI. Okay, so the point of intersection, we're going to look at line 2, 242 plus S131, and S is equal to negative 2. So we go P equals 242 plus negative 2, negative 6, negative 2, and we get P equals 0, negative 2, 0. So that's where they should be intersecting. We should be able to show that that lies on the other line. Let's draw and demonstrate, because that's what I would recommend that you do when you're doing this work. So 242 and 131. So P2 is 242, M2 is 131. The first one was 103, so P1 is 103, and M1 was 2424, and we said it had to be 6. That was the value that we said it should be for C. So we go line P2, M2, line P1, M1. And let's get rid of the direction vectors because they can be a bit confusing. And you see that those two lines do intersect at exactly the point we said they should, which is 0, negative 2, 0, which is that point where they cross. Okay, so everything's good there. Well, we're at the 40-minute mark. I think we should be okay here. So find a vector equation of the line that passes through the point of intersection of these two lines and is perpendicular to those two lines. Okay, so for this one, I'm going to just give you the setup. I'll let you finish it, but to solve this one, you need a line with the following. You need the vector equation of a line. And the vector equation of a line is that r vec equals ro space vec plus t, and let's not use t because it's already been used in the earlier equation. So let's say ts, and I forget what's the other one they use for a plane. Don't want to use r. What's a letter we haven't used? K, sure. Times the direction vector. Okay, and where k is some real number. All right. So to solve the question, you're going to need those three things. So let me tell you how to find each one. RO, so RO vec is equal to the point of intersection of the two lines above. So go ahead and use what you know to get the point of intersection. The direction vector has to be perpendicular to the two lines, right? So the direction vector is going to be, from what you're going to do is the direction vector of L1 times, so cross, right? Cross product, direction vector of L2. So cross the two direction vectors, so 3, 2, 1 and 1, 2, 3. Cross those. That will tell you the direction vector of your line. Doesn't matter if you cross L1 and L2 or L2 and L1. Doesn't matter if you reduce it or don't reduce it. Any one would be right. Okay, so I'm going to leave that one with you. I think you're capable of doing those two things. Determine if the lines are skew. Okay, lines are skew if they are non-parallel, but nevertheless don't intersect. We didn't do one like this, so let's quickly do this one. So M1 is not equal to K M2, right? And you can see that pretty easily just looking at them. To get from 1 to 2, you'd have to multiply by 2, but then if you multiply this by 2, you get 4, not -1, so they're not parallel. So what we're going to do now is just the same thing we would have done in any other question. We'll try to make them intersect. Work with the x parameter first. 5 plus s equals 2 plus 2t. Therefore, s equals 2t, take away 3. Then move to the y parameter. Okay, in the y parameter, you have -4 plus 2s equals -t. We know that s is 2t minus 3, and this has to be equal to -t, so we get -4 plus 4t, take away 6, equals -t. Bring everything to one side, we get -10 equals -5t, and therefore t equals 2. Okay, we go back to the x parameter, and we sub in t is 2, so we know s is 2t minus 3, so s is 1. 2t would be 4, take away 3 is 1. Quickly double check that I did that right, but I believe I did. Now what we do is we go to the z parameter, and we just check the work. Okay, so in the z parameter, what we want to do is we want to show -2 plus 3s equals 1, take away t, and we plug in what we know. -2 plus 3 times -1 equals 1 minus 2. -2 plus -3, so I'll just say subtract 3, is equal to -1. -5 equals -1. This is untrue. Therefore, there are no solutions and the lines are skew. Okay? I guess it wouldn't hurt to quickly draw this one. So P1 is 5, -4, -2. P2 is 2, 0, 1, M1 is 1, 2, 3, and M2 is 2, minus 1, minus 1. Now what we showed here, they are not parallel, and yet they clearly do not meet. Okay, so therefore they're skew. Alright, now, when you know that two lines are skew, of course we're not satisfied just knowing that they're skew. We want to know how close together do they get. So determine this distance between these skew lines, this one and this one. Now again, the skew lines thing is what we're going to do is we're going to project a vector that joins the two lines onto the normal. And what that would do is it would ask how far, right, are these 2 points, if you cast a shadow from these 2 points onto the normal, how far along that normal would the shadow from these 2 points go? Now, skew lines have a unique normal, the same way that a line in 2 space had a unique normal. So you can do the projection technique. You couldn't do the projection technique in 3D between a point and a line because you didn't know what normal to use. But you do know what normal to use here. You use the normal that is, is perpendicular to both of the two lines. And, so you get this by crossing the two of them, right? So it's P1, P2 dot n over n, and n is the cross product of the two lines. Okay? So I'm going to do one of them. I don't think I have the easiest time showing you why this works. I mean, I can maybe try and work on a demonstration I can release tomorrow, but I don't think I can create it this second. What you try to do is, because it's hard to understand how a projection works in 3 dimensions, right? How does it cast a shadow? Let's go ahead and do the question, and then we'll comment on what it looks like. So here's what what we can do here. So point 1 is 5, negative 4, negative 2. M1 is 1, 2, 3. Point 2 is 2, 0, 1, and M2 is 2, negative 1, 1. Okay, so again, you see the lines are skew, and their closest point is probably like around here somewhere, right? So if we made a point on this one and this one, and then we did a segment B and C, so the distance there is 2.7. I can shrink it. I can shrink this a little bit more. Looks like I can get it down a little bit lower. So I want them to be like perpendicular and straight across from each other, right? So like probably something in this neighborhood. So 1.31, 1.19. Like you can see, I'm getting them a bit shorter together, but probably can't do much better than this. At least doing it manually. Well, there's a 1.17, right? So something kind of like that is the shortest. Our answer is something like that, right? Where those two are going to be the shortest points. So how do we get that? So the idea is to project any vector that joins the lines together. We're calling this vector PQ. Project any vector that joins together onto the common normal. The common normal will be found by crossing the two direction vectors. Okay, so PQ for us is easy. What you do is you just do destination minus origin, and you already know 2 points that would work. The 2 points that are in the lines, right? So 5. Let's start the other way. So 2, 0, 1. Take away 5, negative 4, negative 2, and what we get there is 2 take away 5 is negative 3, 0 take away negative 4 is 4, 1 take away negative 2 is 3. Okay, so there's our vector PQ. We just created a vector that joins the two lines together. What we did is we picked 2 points that we know one is on each line, and then we just did destination minus origin. Now the normal vector is going to be m1 times m2, and we're just going to cross them. Okay, so take m1, so again, start with the 2, then the 3, then the 1, then the 2 again. Negative 1, 1, 2, negative 1 again. And we go through and cross each of them. 2 subtract negative 3 is 5. So let's say n. Okay, 2 subtract negative 3 is 5. 6 take away 1 is 5. And negative 1 take away 4 is negative 5. So my theory is that 5, 5, negative 5 is the perpendicular vector. Now again, you know, it probably wouldn't be a bad idea to reduce it. Why don't we just reduce it? We'll make it parallel, right? It doesn't matter. We're projecting onto this vector, so the length will be taken care of later. It might not be a bad idea to check my work by dotting with both direction vectors and making sure you get 0 both times. So 1, 1, negative 1, dot the first direction vector, 1, 2, 3. You get 1 plus 2 take away 3, which is 0. And then we get 1, 1, negative 1, dot 2, negative 1, 1, which is 2 take away 1, take away another 1, which is also 0. So I'm pretty sure I've got this right. Now what I want to do is I want to project, okay, PQ, project PQ, oh sorry, project onto N, oh my goodness, okay, project onto N vec. There we go. I want to project PQ onto the normal, and then I just want to find that length. So remember how to do this. You do PQ, so vector PQ, PQ dot N, and then you divide by the magnitude of N. If I could ever type this. Let's bring the PQ and the bullet up so that it looks more familiar. Okay, so we're going to project PQ onto N. What you do is you simply dot PQ with the normal, and then you divide by the magnitude of the normal. In our case, the magnitude of the normal is pretty easy because we reduced it. Is just equal to square root of 3, right? Because it's 1 squared plus 1 squared plus 1 squared, and then square root the whole thing. So what we're going to do here is we're just going to go D is equal to PQ was negative 3, 4, 3. We need to dot that with 1, 1, negative 1. And then we need to divide this whole thing divided by root 3. Okay? And what we're going to get here is that D is equal to negative 3 times 1 is negative 3. 4 times, so negative 3 plus 4, take away 3 again is negative 6, so negative 2 over square root 3. Oops. And then we remember that a negative in a scalar projection means direction, not magnitude. So we say this is why the formula has an absolute value on it. D divided by square root 3. So 2 over root 3 is what I'm saying is the shortest possible distance between those two lines. Now, 2 divided by square root 3 is 1.15. So you can see that if I were better at lining these two up, I would have, I could have done this a bit better. So if we draw a sphere located at point C with a radius of A, we should be able to show, and we'll just hide point B for a sec, we'll zoom in a little bit. We should be able to show that that sphere is exactly the right, distance away, the closest that you could ever get. Right, so something like that. Sorry, this segment is making it look confusing. Again, it's difficult to visualize this properly, but you can kind of try to see what I'm trying to show you here, right? That sphere represents the shortest distance between the two. It might be easier actually to work with a circle. Point C, radius A, direction vector M1. So let's work with a circle instead of a sphere. Kind of see that circle. Right, so if I'm there, it's too far away. Zoom in a little bit. Bring it right just down there. That's actually missing the line, so that doesn't really count. Something like this, right? Sorry, let's try to fine-tune this. Right, so that's about it. It's the shortest distance you can get from the two objects. Okay, so remember, you already know this formula, and you know this idea. You're projecting a vector onto a normal. That's always the way you get the shortest distance to something. The reason you couldn't use it when you were doing point to line in 3D, let's just review for a second. So let's make a quick shortest distance table. Shortest distance. Point to line in R2. Point to line in R3. Point to, or skew lines in R3. Okay? So second, sorry, insert, let's insert to the left. Okay, case, unique normal. Do they have a unique normal? Yes, no, yes. So, technique, project PQ onto the normal. P equals the point, Q equals any point on the line. A point to line in R3. They did not have a unique normal, so you'd use a parallelogram. Find the height of the parallelogram. You go back to that lesson if you want to review that one. We will talk about that one again, but for now, let's not go too deep into it. Here, project PQ onto the normal. P equals any point on L1. And Q equals any point on L2. Okay, so notice, what does this have in common with a point to line in R2? They both have a unique normal, so you can project onto it. You can't project onto a normal in R3 with point to line because you don't have a unique normal. So that's why the techniques are different. But I want you to see that this one and this one are really just the same thing. Okay? And that's what all of that stuff demonstrates. So there's a couple of questions down here for you to try. Please post any questions. And this concludes Unit 8. We'll be moving on to Unit 9 next.